I was contemplating with Dan Friedman, a friend of mine, old friend, that in fact I've been computer programming for over 50 years, and as a consequence I've fallen into every possible hole that one could fall into, and in fact manufactured lots of holes that I've walked into after the fact. And so I suppose one of the things I've been discovering is that the important thing to do is tell people how not to do that. Okay, and that's fun. But today I really want to talk about something entirely different. I want to talk about the fact that most of the time we think of these computers as doing work for us. That's our job, right? On the other hand, computers do something really special. The computer revolution changed the way we think, and that's indeed something that we wrote about in SICP in the preface. It said the computer revolution is a revolution in the way we think and the way we express what we think. Okay? And in fact, I want to think of that as an expressive medium in the wonderful way that we saw this morning with music. Okay? That in fact there are many things you want to express, and one of the things that is to re-express things like music in a way that you can understand it. Now, the particular things I want to talk about today are not specifically non-technical, or maybe music is very technical. I got to be careful. That was the wrong thing to say. Mozart would have considered it very technical, or Beethoven. But it's something else. What I want to talk about is the things we normally traditionally think of as technical. As you probably know, my first application of programming that was sort of any significance was, gee, I wonder what that's doing there. Thank you. Was to teaching electrical circuits to students. Back in 1974, when I started teaching in 73 at MIT, and I was teaching electrical circuits analysis. And one thing that I observed was that the ways we teach students really have very little to do with the way we do it ourselves. Okay, that's sort of very strange. We teach them to write all sorts of equations down and things like that. And by golly, if I tried to write down the equations for this 4-transistor rather poor amplifier, it's got terrible crossover distortion for those of you who know enough about amplifiers to know that. But if I would say that those equations are pretty much unsolvable by any human in person. However, what happens is that real experts can look at this and say, oh, I see, there's a complementary pair over here. That's a unity gain power stage. There's a gain stage, voltage gain stage here, and there's a stage here which takes input and produces feedback, gets feedback from the output compared with the input. So, gee, this is probably pretty easy to understand. This is a linear amplifier, we hope. And well, we can assume in the linear case that all these transistors have their emitter base regions are forward biased. Okay, and as a consequence, they're about 0.6 volts. Now, watch what I'm about to show you is something which you're not supposed to understand what I'm doing as an electrical engineer, but you understand what I'm thinking. Okay, so I'm about to do a quick analysis of this for a second to just show you what I'm doing here. I'll do a DC bias analysis. I've got a 15-volt rails, plus minus. That means there's 30 volts from one end to the other. I've got a 30K resistor here and a 3K resistor here, so I've got a voltage divider, which would be 2.73 volts over here. 0.6 volts down is 2. I can't do my arithmetic, but I wrote it down. That's nice. I never could. So it's 2.73 volts across this resistor. Okay, so it's 2.13 volts over here. Subtracting 0.6 is hard for me. Okay, so then that means that I sort of know how much current's going through here. It's basically 2.13 milliamperes. That must be coming from up here, but there's other things going on. There's only 0.6 volts across here, so there's only 0.6 of a milliampere going through here. So some of the current must be coming through here. That current, which is, I suppose, and I wrote it down here because I did the subtraction, 1.53 milliamperes, goes through this 10K resistor, so that means there's about 15.3 volts from here to here, plus the amount that was here, which is 2.13 above the minus 15 volts, gives me about something like, what did I write down there? Gives me 2.43 volts over here, so this is sitting a little high, giving me 24 milliamps through there. This transistor must be turned on. As a consequence, this must be at 0.6 volts above this, and so now I know all the DC bias conditions for this device. Okay? What I've done is no equations. Okay? That's an important thing. That's the way I think the only reason people can think is because they can do this. Okay? This local analysis, okay, producing answers that are approximately right. I'd have to check all these to make sure that I didn't make any terrible assumptions. It could be the case that this transistor is not really biased the way I thought it was. It could be that the current going through here is big enough so the beta, the amount of current going into here changes the voltage across that voltage divider, and that would be a problem, enough so that it would change my analysis. But it turns out that it isn't. It's going to give me an accurate answer. In fact, from doing a little incremental analysis here, which I'm not going to do, I can tell you this has got a gain of about between 10 and 11. Okay? It would be about exactly 11 if it weren't for the fact that there's a lot of current coming through here, okay? Because it's a 10K and a 1K resistor. But it's going to be less than that. Okay, so that's the sort of thing that I want the students to learn how to do. And as a consequence of that, what I really cared about is, gee, how can I write that down? That doesn't fit the node method or something like that you might learn in an electrical engineering class. It doesn't capture that kind of idea. So what I did, and first of all, I got a hold of a wonderful undergraduate from Harvard by the name of Richard Stallman. And he and I wrote a program that basically simulated what I did. And also could get an answer saying the reason why you got this result was it, and it backtracked and gave the deductive chain. Okay, that was nice, and we could give that to students, and the student could read it. Now you see, read that program and understand it, and then the student could do what I could do. That's the goal. Now, I've been doing that all my life. That's been my real goal, is to transform things that are hard to understand into things that can be easy to understand, and programming has been one of the tools in doing that. So recently, Jack Wisdom and I have been working on basically advanced classical mechanics, the kind you do in sort of beginning graduate school in physics, for example, or advanced undergraduate. And then recently we did a functional differential geometry book. And I want to talk about that sort of thinking, which is a lot harder, I admit, than the electrical circuit thing I just showed you. But I'm going to talk a little bit about that, how programming helps you understand things that are usually written very poorly. No matter how good the authors are, it turns out that the traditional methods of writing these things are terrible. Let's see, what is the problem really? The problem in learning things like electrical engineering and physics is that we have to learn several things. They're expressed in mathematical language, mathematical notation, and mathematicians and physicists have shared culture. The reason why I can talk to you and you can understand me at all is because we're almost identical. We have an enormous amount, we're almost identical physically, and we're almost identical in our experiences. I mean, if you talk about the really grand scale of experience, in which, as a consequence, it takes only a tiny little increment of information to produce a big effect in transferring some information, a big piece of the data structure in my mind to a piece of data structure in your mind. Okay? But anybody who shares cultures know that it's hard to talk across cultures. And what happens is that mathematics has shared culture, physics has shared culture, and the difficulty is that they talk to each other in ways that depend upon the sharing of that culture. Trying to get an introductory student to understand that is very hard because they have to simultaneously learn the culture and the language as well as the content. As I like to say, it's like trying to read Les Miserables when you're learning French grammar. Okay, it's that kind of problem. Okay, so I'm going to show examples of that to begin with, and I'm going to start with something very simple, but fundamentally, here's a nuttiness. This is the sort of thing that we do to high school students. Any logical high school student would throw this back at you and say this is nonsense. Therefore, the math is not worth learning. Okay, you can see that, right? Because indeed, this is contradictory to the rule that's implied by that. Okay, that's not what we mean. This is fundamentally an idiom. Okay, it's an idiom of a normal, natural language invented by mathematicians to talk to each other. Okay, and we do all these things in our natural language all the time. An example I wrote down today is, I only wrote 2 sentences. Or I wrote only 2 sentences. Okay? We both agree that probably they meant the same thing. On the other hand, the only wrote 2 sentences. I could have spoken them. It's a different idea, right? So the language is not making the right distinction, at least unless I put in the inflections and intonations and stuff like that. So idioms make it hard. Here's a piece of idiom, but that's not the real problem. I mean, let's look at something even more serious. Let's get down to something like in elementary physics that you might learn in your first physics class, there's this Newton's force equals mass times acceleration idea. Of course, he didn't have vectors. Vectors were invented later, so he had to be much smarter to figure that out. Okay, but you know, what is this? Look, I have some trajectory, and the trajectory is a function of time. It says where something is at every moment in time. And what I really have to do is find out whether or not the trajectory, when substituted in with a particular force law, satisfies this equation. That's the purpose of this. This is what's really meant for any particular problem. This is gravity. Okay, so a central field in gravity. But it could also be some other force law, and then you'd have some other kind of system, and it's a different thing. Okay? And the students have to understand that. We never tell them this. We never tell them what this is. It's a macro with some untyped and undeclared parameters, and we don't tell them what the parameters are. So this is not easy to understand. Okay? Now, it gets worse. This gets terrible. Here's something which we learned Leibniz notation. And Leibniz notation for derivatives happens to be a disaster. Okay? Here's an explanation of how it's a disaster. Look over here. Okay, suppose we have a function e, which is defined with the formal parameters x and y. As a programmer, I understand this. You see, formal parameters x and y. Okay, which happens to be defined as f of two things, g of x and y and h of x, y. And supposing I want to know the partial derivative of e with respect to x. Okay? Well, what do we write? We write a chain rule. We learned that in one of our second calculus class, I suppose. So we have to invent symbols u and v, okay, to represent the insides. And then we write here the derivative of this object with respect to x happens to be the derivative of f of u v with respect to u times the derivative with respect to x. That's fine. Plus derivative of u v with respect to v times derivative with respect to x of v. That's okay. But then we shorten it. This is what you actually see in the book. Okay? This is what the teacher puts on the blackboard. Okay? But that's terrible. What is this f? This f and this f aren't the same thing. Okay? This f is a function of what? Okay? Okay, so something that's missing. They don't put in the good stuff. Okay, what's really meant here, if you want to look at what the actual chain rule, the correct chain rule, it's none of the above. It happens to be this. Okay? Because what it's really saying is that I'm inventing two objects, u and v, that I'm going to take a derivative with respect to u here, and then I'm going to substitute u having that and v having that. So there's a substitution done, and then I have to take the derivative of this, and these have to be evaluated at the right place, which this does. Okay? And now you see what the chain rule really is. And you only think about this when you're trying to write a program and it doesn't work. That's the real story. Okay, so this is kind of disgusting, and I've encountered this a lot. Having gotten my degree in mathematics, both degrees, bachelor's and PhD in mathematics, I've been through lots of classes where I sat there and scratched my head for a long time. I got an A in the exam, I didn't have the foggiest idea what was going on. When I really analyzed the problem, it was because it wasn't apparent what those expressions were. You know, I learned how to manipulate by rote. Okay, get the answer, and by golly, I didn't really understand. The real thing is that a lot of that stuff was left out. Now, I don't like that. I want to tell students what's going on. So of course, I always learn things by writing programs. So let's start with something where now you're going to start seeing hairy stuff. I apologize. This talk is hairy. Okay? But I'm going to do my best to make it at least a little bit fun. Okay, so let's go. Let's talk about light. I'm going to get into advanced classical mechanics right now. We'll get into general relativity later. Okay, so it's just starting. Okay, but here. So here's the normal way we write the equations of motion for a general Hamiltonian system. Okay, it's called Lagrange's equations, Lagrange-Euler equations, because they were invented jointly by Euler and Lagrange, and they're solutions of a variational problem. There's an idea that the way in which you write the properties of a system that's going to you're wondering about, like the motion of objects, okay, is that you produce a function which happens to have the property that small variations in the path, okay, that you might test in there might have, it will be close to zero, closer to zero value, change in the value of this function if it's the right path. That's the idea as a variational idea. And what do you mean by motion? Well, here's an example of a dense book, okay, and it spins like this, right? Everybody understands it spins like that. It also spins like this. However, go try to spin it like that, and it flips. It's almost impossible to spin it so it doesn't flip like this. Okay? This is one axis, a different axis. The intermediate moment of inertia axis is unstable. Why is that true? Well, that's the kinds of thing we study in mechanics. That's what I'm just giving you an idea why we're. So what you'd write down is something which is called the Lagrangian function, which is a function of time, coordinates, and rates of change of coordinates, which may be I-dimensional space. In this case, it's, I suppose, has 6 dimensions for that because it's 3 position and 3 orientation dimensions. And we're going to write down this equation, which turns out to produce essentially Newton's equations of motion, but in a coordinate-independent way. Unfortunately, this equation doesn't make any sense at all. And that's because Lagrange is a function of 3 variables. The partial derivative had better. Where did this q dot come from? What's the path? The path isn't shown here that I'm trying to test. I have to make sure, I have to find out whether or not a particular path satisfies the equation. It's not there. But in any case, I've got this partial derivative should produce a function of 3 variables. What's this d by dt doing? It's looking at functions of 1 variable at best. Okay? So somebody had to substitute the path in the right place. It's all implicit. In fact, what was really intended was this. Okay? There's the real equation. And you only discover that when you're writing the program, as I'm saying. Not kidding. Okay? So here's the real equation. The real equation written in Leibniz notation, which sucks, is that you introduce these extra parameters, okay? And now you have to write down that there's a path W, which I'm testing for acceptability, that's possible path of the system. And I take the derivatives, this partial derivative, which makes sense now, substitute the path in, take a time derivative, because this is now a function of time only, this object. And the same thing, this is a function of time only, and that had better balance. This is basically saying the rate of change of momentum is minus the forces. That's what it's saying. Okay? So it's F equals ma. On the other hand, there's no reason for us to write this in this crazy ancient notation just because Leibniz invented it. And it turns out it's painful and complicated and it leads us down bad paths. What we can do is I'm going to slowly abstract this into a nicer notation. The notation was invented not by me, but by a wonderful guy, a wonderful mathematician by the name of Michael Spivak, who wrote a great book called Calculus on Manifolds, which if you haven't looked at that book and you think you understand calculus, you don't until you've read this book. Okay? The whole book is an intention. Basically, the goal of the book is to prove the Stokes theorem. But the important thing, which is the generalization of the fundamental theorem of calculus. But the cool thing is that he completely discards this notation. It's page 44. He complains bitterly about Leibniz notation and throws it away. This book was written when I was sort of an undergraduate, 1960s. So first thing I'm going to do is I'm going to get rid of those two by using positions. Because the only purpose of those q and q dot was to integrate the position in the arguments of a function. Okay? This sort of become combinators. Okay? And then the next thing I'm going to do is make a functional derivative, which is the derivative is really, I'm going to get rid of the expression here. Because I don't need to introduce that extra x. This new function, df, is a function of time. Okay? That's what it is. And then I'm going to invent a thing which takes the path and gives me instead a path through the state space, the space of time, position, and velocities. And that's what that is. Okay? Because now, once I do that, I can make the next step here and say Lagrange's equations now look like this, which is pretty good, but I still have an expression derivative there because I have an implicit t that I put in. Okay, just so I can refer to it. And now I'm going to since I can use composition of functions, we're in a functional programming world here, okay, then I can take this and make this a derivative. This derivative is now a derivative of a function of one argument, because this is a function of one argument that produces 3 arguments that go to here. Okay? And this is completely unambiguous. It leaves nothing out. It's the truth. Okay? That is what Lagrange's equations really are. Okay? And not only that, they transform instantly into a programming language so they can be executed. Okay? It's quite literally one-to-one correspondence with somewhat augmented scheme. The augmentation is that there are derivative operators. Okay? That's all. And that's interesting. And of course, this guy is just a higher order function. Gamma of W applied to T is just a thing which makes the data structure up. Up is important because the derivative with respect to an up is a down. If you want to know things about that, it has to do with tensors, and we can talk about that later. We may have to. Okay, so this is the nice thing is, you show someone this, maybe they don't understand that notation, but you show them this and they know how to program, boy, now we know what it says. This is a thing that's producing for me the residuals of Lagrange's equations. That means the thing that should be 0 if they are satisfied is the discrepancy if I put a path in that doesn't satisfy the thing. So for example, here's just a simple example coming up. I'm not going to tell you why this is the Lagrangian of a harmonic oscillator. A harmonic oscillator is a spring and a mass. Just, okay. But I'm not going to tell you that. You'd have to take my class. But a harmonic oscillator has a difference of kinetic and potential energy for whatever it is. And there's a mass parameter and a spring constant parameter involved. And I could write down that harmonic oscillator Lagrangian, okay, just like that. And by the way, this works for any number of degrees of freedom. That's the number, the dimension of the space. So I could have a harmonic oscillator in any number of dimensions. This will all work. Okay? But I know for one dimension that the solution, general solution, is x of t is a cosine omega t plus phi. It means it oscillates sinusoidally with some unknown phase and amplitude, but with a frequency which is determined by m and k. So I could take that proposed solution. It's a function. I have some symbolic things. These are what you call literals in algebra in high school. Okay, that means I don't know what it's a number. I don't know what it is. Very important. That's one of the great advances in the history of humanity is the invention of literals. Okay, but once I do that, I can plug that in. Okay, and out comes, well, actually how it comes is scheme code representing this expression. But in a fit of anger, Hal Abelson, one afternoon, got mad at me, I don't know why, and he wrote a program that made a LaTeX out of this. Okay? And so we can, if you just say, don't say show expression, if you just say this much, you get the scheme out. But if you say show expression, out comes this. Okay? So that's the turns out it's not very hard to write this program, but I never understood it because I don't understand LaTeX very well. Okay, but what you see here is that in order for this to be 0 always and a not 0, okay, because cosine's not always 0 no matter what, okay? So in order for this to be 0, k minus omega square, m omega square had better be 0, which tells us the frequency, the angular frequency of a harmonic oscillator. Okay, so that's just an example of a simple thing. On the other hand, we could use literals even more seriously here, and we could say, and the only reason I'm using a harmonic oscillator is because it fits on the screen. I mean, it's much more interesting when we're dealing with the motion of the planets and, you know, with expressions that are 10 pages long, and then, by the way, infix doesn't work. I don't know if you realize if you've got 500 terms in the what's called the disturbing function of the planet Mercury, okay, based on all the other planet interactions and things like that, you end up with a 500-term object, and there's no way you're going to write it in an infix, but if it's in prefix, it at least lines up all the terms. Okay, so you can find the ones you want. Emacs does that for me. Anyway, so what you end up with is the residual is Newton's equation of motion for the harmonic oscillator right there. Okay, so that's the kind of thing that we're getting into here. Okay, so now what that gets me, of course, is that the horrible original Lagrange equations that we saw in the book and what people told us and things like that had all sorts of crap, missing parameters, type error. But when you're forced to program it, end up with something which, by the way, is just as short. That Lagrange equation that you saw here is no longer than in number of characters than the one that's in the that's the traditional way. If you put in, of course, the superscripts for the index and all that, it's the same. Okay, it's no harder to understand. It's just that it's not traditional. Okay, but I think prefix is not traditional either, and I like it better. Oh well, sorry, we're in a place where people seem to like syntax. Okay, so on to I'm going to get on to the next hairier thing. Okay. Oh, I got one more quick example here. Oh no, I've been there. I'm sorry. Here's the next thing. So supposing I have free motion. That means motion with no forces. Okay. Well, that's just the kinetic energy, because the potential energy is where I derive forces in a system of that conserves all the interesting conserved quantities, basically the universe. So here's the kinetic energy, 1/2 mv square, for a particle that's just sort of in free motion. You know, and I can imagine being, for example, a nice thing might be a frictionless croquet game. You can imagine someone playing. On the other hand, we all live on a sphere. So let's consider a frictionless croquet on a sphere. Well, one thing I want to do is that I have to make transformations of coordinates. I want to say, gee, this is forced to be on a sphere. So what I have here is I have a transformation that takes a state, pulls out the coordinates, gets me, and gives me the transformation. This is the x, y, and z of a three-dimensional representation of the surface of a sphere. Okay. So I've just transformed the coordinates there. Okay. And now another thing so this is in terms of a two coordinates into three. Just to notice that. Okay. Then I can use that. I can make a thing that transforms any transformation of coordinates, any one given at all, into a transformation of states. States, remember, are time, coordinates, and the rate of change of those coordinates, the velocities, the generalized velocities. So here you've got a computation which I'm not going to explain. It's pretty easy. Again, remember, I'm not teaching you physics here. I'm showing you how programming helps. So I write down this thing, you see, which is the general transformation of transformations of coordinates into transformations of states. Okay? And if I compose those, okay, I can get the Lagrangian, a Lagrangian, not there's many Lagrangians for this, but I can get a Lagrangian for the game of croquet on a sphere, on the surface, which is true anyway about us. Okay? So here's what the Lagrange equations unfortunately get very complicated. I left it as a mess. I don't want to show them to you. They're, you know, you can do it by hand. You can. This is no longer not yet as bad as you do in celestial mechanics, but you can do it by hand. It's actually amazing what people did in celestial mechanics in the 19th century and the 18th century. Oh boy. Leverrier figured out that Mercury had a problem of, was it 43 arc seconds per century of error in the precession of the perihelion, and he must have done math that I couldn't possibly imagine by hand. Okay, and it was, you know, I don't understand how people ever did that sort of thing. They were probably very good at that sort of computation. I can't compute, so I got into computing. So anyway, the reason why I wanted to get into this is because I want to show you something about free motion on a sphere. Okay? Even though I can't show you the old equations because they won't fit on 3 or 4 slides. Let's talk about parallel transport. Okay? Now, supposing you're sitting at the North Pole, and you have a stick, and you're going to walk along the Earth. Okay? But the first thing I'm going to do is make a scratch parallel to the Greenwich meridian. Now I'm going to walk down the Greenwich meridian for a long time till I get to the equator, holding my stick in front of me, pointing south. Then I'm going to turn left, but keep the stick pointing south, And I'm walking along the equator until I get 90 degrees east, I suppose. Then but I keep it pointing south. Then I'm going to start walking north along the line of longitude at 90 degrees, holding the stick pointing south still until I get back to the North Pole. Okay? When I get back, if I compare where the stick is pointing, it's not pointing the same way as it did before. In fact, it's 90 degrees out. Okay? But I always kept the stick pointing south. So there's something very strange about this. This is what's called curvature. Okay, it's the curvature has the property that actually the amount of angle I change by is basically a function of the area of the enclosed curve I walk along. That's an interesting phenomenon. And when we're walking along both the meridians and the equator, those are geodesics. Those are the analog on a surface, or what we call a manifold, of the concept of a straight line. Okay? It is the shortest distance or the longest distance between 2 points. In a great circle, I could go around the other way, and it's the longest distance if I'm walking that way. So, maybe I'm going to show you now a nice static thing, which is the equations for geodesics. Okay, okay. I know this is a little weird because you have no idea what this is yet, for most of you, except for the physicists in the audience, okay, or mathematicians, I suppose. But in general, the idea is if I walk in a direction pointed by my stick, but I always keep the stick parallel to itself as far as I'm concerned, then I'm walking a geodesic. Okay, that's what a geodesic is, and that's what this says. If V is the velocity vector field on the sphere, or whatever it is, then this weird symbol called nabla, which at least in LaTeX, presumably it's basically del square, it looks like, in simple coordinates. But this symbol is saying that the direction of the velocity is the velocity. Okay? But this is not very precise because it turns out that that's, again, the telegraphic notation that leaves out all the detail. More precisely, what's going on is something that looks like this, which is I've got a curve I'm walking along, okay? And that there is a unit vector field in the time direction, saying I'm walking forward in time or backward in time or whatever, but I'm walking along in time. And then I have a thing called the differential of that path, which is being evaluated. It measures the walk along, okay, in time. And this is actually more precise. And then if I expand it so this is coordinate free, if I do it in coordinates, it looks like something horrible with something called Christoffel symbols and 3 indices. And I don't want to see that if I can avoid it. Okay? But what these Christoffel symbols are about, they describe the nature of the surface. Locally, they say the shape. Okay? And from them, you can compute something called a metric, which is basically the concept of distance and things like that, from those Christoffel symbols. So now, what I'm going to show you next is a little scary, because here's the geodesic equations, and I'm not going to say why they are. This guy is the nabla, covariant derivative with respect to the path, okay, and that's what that symbol is. And there's, this is just, again, translation directly from the code you saw there, the Sirius code. But I'm trying to be very careful that I'm not trying to teach you this stuff. I want you to see what that code is simple, though. It really is very simple, okay? And you can read you can read the insides of covariant derivative, and it's simple. And the insides of differential, and it's simple. Every one of these things is simple, okay? It's something which, of course, it's many pages, but each piece is understandable because it's all there, okay? And so then I can write the metric for a sphere, which is that it's this is in terms of something called differential forms. So these are vector fields, which are piles of vectors all over, comb hair on a sphere. You can't, of course, but the hair points are vectors, and then what these thing is doing is measuring how much of that vector is pointed in the theta direction. Okay? So this is a metric between for a sphere. Okay? And so I can just write it down, and I can write it down very simply. Okay? I can define some special coordinates for it, spherical coordinates, and then write it down in terms of those coordinates. And these are automatically created, d theta and d phi, which are the basis covectors, or basis 1 forms for that system. And now, what I'm going to show you here is the truth. The wonderful thing is that if I take an arbitrary path, okay, on a manifold path from R1 to the sphere, R1 meaning the time, or just a path that's one-dimensional. It doesn't really matter that it's time. Okay, take an arbitrary path on that, and I make a coordinate path out of it by picking the appropriate charts and points. Okay, and I look at the Lagrange equations for that coordinate path for a free particle. Okay, that happens to be the same as the geodesic equations for the sphere. It means it's a perfectly simple thing that you wouldn't be surprised about. That is, if you have free motion on a sphere, that's the same thing as moving along geodesics. And it turns out it doesn't matter if it's a sphere. It doesn't matter how many dimensions this is. If I do this for any manifold for which I have a metric, okay, and for any number of dimensions, of course, computer takes a long time to figure it out. Okay, then out comes the residual is 0, and that's cool. You just proved a theorem for me that would take me days, personally, of computing and getting it wrong 3 times, and then having to say, oh yes, I see where I made this mistake, and I have to compute it again, and so on. Okay, now let's get into general relativity. I will be mercifully short. Okay. The first thing I want to talk about is that supposing I pick a very simple system. Now, those of you who have had some physics know about special relativity, you know that the speed of light is constant. And what that fundamentally means is that no matter who's measuring the speed of light, you get the same answer. Which means if you see a sphere of light expanding, then it's always going to be a sphere from any point of view, even if you're moving relative to it, or to the source, or whatever. Okay? And so what that ends up doing is producing a metric, a funny kind of metric, on the space-time object with 4 dimensions of, say, x, y, z, and t, which looks like it's negative for time. Of course, some people write it positive for time and negative for the other coordinates. It doesn't matter. But the critical thing is that what I have here is minus the c square times the measure of these vector fields in the time direction plus the measures in the space direction squared is going to be the metric for the simple case. Okay? And if you put v1 and v2 equal to each other, then you're measuring the length of a vector, which is the size, say, a radius vector on a sphere of expanding light cone. So this is basically what's called the Minkowski metric. Okay? But now I'm adding in a little thing here. I'm adding a. Okay? What a is 1 plus 2 over the square of c times times gravitational potential, okay, at x, y, and z. Okay, so gravitational potential is like gmm over r. No, gm over r, excuse me. Gm over r is the gravitational potential for gravity field. Actually, I forget whether it's minus or plus. I have to think about that. Okay, that's always a problem. But in any case, what's going on here is, so this is for a weak gravity, where c is very large, which it is. Okay? So like around here, this is basically special relativity. Okay? But gravity does have some influence, however small. And so I'm going to call this the Newton metric. And I'm going to invent the little covariant derivative for it, okay, which I'm not going to explain. Okay, that was that Nobler picture, that upside down triangle. Okay? And then I'm going to show you the interesting thing. The geodesic equations for a space-time with the Newton metric G for potential field V happens to be exactly Newton's equations. You know, if I code this up, which I will, okay, in scheme, and then I evaluate the geodesic equation, and then look at the high order terms, the terms that are the largest, okay, I get exactly Newton's equations. There are other terms that show up later, okay, and this is the standard Newton's equations for motion in a gravitational field, because the gradient of the potential is the force, minus the gradient of the potential is the force, okay, the gravitational force. Okay. Oh my. Do I really want to go there? Yes, I do. Okay. So now, talk a little about the other half of mechanics. Remember, there's a part that has to do with mass times acceleration. That's what I just showed you. Force equals mass. But the other part is where the forces come from. Okay. What are these things that influence motion? And for Newton's world, it's very simple. It's this. It's that the mass density produces a gravitational potential. Okay, this is Poisson's equation. It's a nice way of saying GMM over R square, okay, which you learned in high school. Okay, but basically that's what it is in a coordinate independent way. Okay? And so this is the Laplacian operator of V equals 4 pi g rho. Okay. Well, Einstein had to make up such a thing too, for gravity. And so he dealt with an object. This is the way he wrote it down. This is the Ritchie or Ricky. How does he pronounce that? Does anybody know if the guy's name was Ricky or Ritchie? Ritchie. Thank you. Okay. So that fixes a bug in my head. Okay. Because I've only read it, you see. I've never said it before, or actually never said it in a room where somebody knew, or claimed to. Okay, so this is a measure of the local curvature of the space-time. Exactly how, I don't want to explain. Okay, it appears in two places here. This is the contraction of this one over its two indices multiplied by the metric for the space. This is the famous cosmological constant, and then this thing says something having to do with the density of matter and energy, or actually energy is the only thing that exists because F equals mc squared. So it's the density of energy all over the place. It's called the stress energy tensor. Okay, you can also rewrite it this way. Einstein wrote it both ways. Okay, there's a transformation of this equation into this equation easily enough. Okay, and what I'm going to show you is a derivation that these are the same. Okay, it's very simple. I'll show you most of it. I won't show you all of it because it takes up more physical space. So first thing I have to invent a point in space-time. I'll pick a general potential field. Okay, that's going to be it's from three-dimensional space of physical space, our space, to real numbers. And I don't care what the potential is. It's just some literal function, just like x is a literal number or something. Okay, I have to invent the Ritchie tensor, which I'm not going to explain. It's built out of something called the Riemann tensor, which is built out of the nabla. Okay, therefore the covariant derivative, and so I build the appropriate thing. Okay, and I can compute the time component of the left-hand side of the Einstein equations. So here's time for a typical event, okay? And I get some mess, of which the leading terms are exactly Laplacian of V. That's a nice thing. Computer can do this, okay? Now, the other side takes a little more work. Supposing I take uniform matter density all over, because I'm going to do something like, well, I don't mean uniform. I mean based on a function which is density everywhere, matter density only, not other kinds of energy, not things like pressure and stuff like that, okay, or momentum flows and things like that. Take a simplest possible kind, okay. So that's this, okay. Evaluate the right-hand side of Einstein's equation, which is this thing over here. Okay. Again, you don't want to know why it looks like that. And what comes out is 4 pi g rho. So Laplacian of V is 4 pi g rho in this very elementary case. That's nice for low order terms. There are, of course, corrections due to Einstein. That's why there were 43 arc seconds per century discovered that mattered. Okay, so the computer can do this sort of thing. But better yet, let's get into Einstein's equations really. So here's Einstein's equations for a metric. Einstein's field equation. It's taken, you build an Einstein tensor at school, which is the left-hand side of the equation. And the Einstein field equation is the Einstein tensor plus this L stands for the big lambda, which is the cosmological constant. Unfortunately, I'm not allowed to type LAMBDA, and I don't have the lambda symbol in my terminal, so I use capital L. And that's 4 pi, it's 8 pi g rho times t, that tensor. So here's the residuals for the Einstein field equation, okay? And I'll now introduce a metric, which is let's do something nice. Supposing we consider a universe that's everywhere the same. That's, what's called isotropic and homogeneous, which it seems to be on a large scale. That is, if I go to some place far away, a couple of gigaparsecs, okay, the universe looks sort of the same at the scale of gigaparsecs. Okay, there's clumps of things called galaxies and galaxy clusters and stuff like that, and voids and all that. But at the scale big enough, it's sort of pretty uniform. Everywhere you look, there's galaxies that look sort of the same. And so we're going to have a metric for a space that's like that. And this was invented by a guy named Friedman. Actually, Friedman, Lemaitre both invented this metric way back in 1920 something. I wrote it down here. It's just after Einstein. 1922, Alexander Friedman. Okay? So that was a homogeneous isotropic universe. And also, we can consider a universe that's uniform also in the density of material. Okay? So we're going to talk about the right-hand side. And so here's the stress energy tensor appropriate for what's called a perfect fluid, which is basically something which is uniform in sort of energy density and also invariant, has to be invariant under special relativity. Okay? So now, if I let my computer crunch all night, my laptop, that's amazing, my laptop can do this, okay? It will come up with the Robertson-Walker equations for the evolution of the universe. Okay? I've had them printed out by Hal's printer as opposed to in prefix notation, because it would be longer in prefix notation, because again, one of the reasons why things are longer is because we tend to indent them and all sorts of nice things like that. But in any case, it would be harder to read, and this is very familiar. This is what they look like. Okay? Comes up with these equations. And once you have these equations and you say, oh yes, if the density of the universe on the average is bigger than some number, then it will collapse. And if it's smaller than some number, it will expand forever. And if there's sort of a nice balance, which it seems to be at, which seems to have something to do with the cosmological constant now and all that sort of thing. Okay? But this is the basic equations of cosmology. So the point is not that this is some new derivations or anything like that, or not new information or anything that extreme. What this is it makes comprehensible what are otherwise badly expressed in traditional ways. And the reason why it's badly expressed is because, again, I'll go back to it, it's because the people who express it are perfectly competent, but they're talking to each other. Okay, and they all have assimilated a huge corpus of culture. And so they expect the students to pick it up. And I don't do that. Okay, it just doesn't make sense. I want students to understand things because I give them a clear exposition. Okay? And clarity sometimes needs programming, because the real reason is the damn computer is not going to let me get away with it. That is, if I write a program that doesn't represent something sensible, I get an error. Okay? And I don't care about type systems. That's irrelevant at this level. Okay? Maybe it isn't. I don't know. I mean, I'm sure you guys would love to write wonderful categories and things that make all this very clear. But as far as I'm concerned, the clarity is not in the categories. The clarity is in the content, okay, in this situation. And so I'm going to conclude with I think my real conclusion is the same Marvin Minsky came to when I was an undergraduate. Okay? And this is, I'll read it to you. A computer is like a violin. You can imagine a novice trying first a phonograph and then a violin. The latter, he says, sounds terrible. That's the argument we've heard from our humanists and most of our computer scientists. Programs are good, they say, for particular purposes, but they are inflexible. Neither is a violin or a typewriter until you learn to use it. And that's all I have to say. Mm-hmm.